Hello everyone, this is Dr. Webb and welcome to this calculus video. In this video we're going to be talking about a trick that was developed by Isaac Newton hundreds of years ago, which is called Newton's method, and it is an incredibly efficient way of estimating when functions hit certain values. So let's jump right in with an example. Okay, so let's say we want to find a very accurate decimal representation of the cube root of 10. We really need to know the decimals. We're doing something practical. We need to know what the numbers are. As many decimal places as we can get. Okay. So let's kind of walk through how we're going to do this. So this is a graph. It's really rather hard to get cube roots, but cube roots really, that's the inverse function of that is cubing something. And so this is the graph of y equals x cubed. And if I know the decimals for something, it's not very hard to cube something. You know, just multiply it by itself 3 times. And so instead of trying to find the cube root of 10, I'm going to try and figure out when x cubed equals 10. And so we have the red line across at 10. And so it looks like it's happened somewhere between 2 and 3. And so what I'm going to do is I'm going to pick a value that seems to be close and work from there. And so one value that I know pretty well is that x cubed goes through, y equals x cubed goes through the point 2, 8. So let's use that point, 2, 8. And now it's difficult to figure out exactly where x cubed crosses 10. But from this point at 2, 8, I can find a good line that's closely approximates this function there, and I can figure out where that line crosses 10. And so what line am I going to choose? Well, of course, I'm going to choose the tangent line. So this is the tangent line going through the point 2, 8 of the graph. As you can see, it stays pretty close. And since this is just a line, it is really simple to figure out, given the equation of a line, it's really easy to find x values that hit certain y values. So I'm going to use this tangent line to figure out this point. So I can go through, calculate that point right there. And if you look, this is looking pretty close. And so if we zoom in, so here we are zoomed in quite a bit, you can see the tangent line's a little bit off, but we're really pretty close. So let's say I want to make this better. Well, how am I going to do that? Well, I have this new x value. Let's call that x value, let's use green because it's in green. Let's call that x value x1. I can plug this back into my original function, y equals x cubed. And so I get this new point on here. And so this is the point that at x1 cubed, and then now that I know x1, I can do the same trick I did before. Take the tangent line through that point, and then look where it crosses 10, and now we see we're even closer than we were before. In fact, it's so close, it's really hard to tell the difference between the two in this picture. Okay, so let's go through algebraically exactly what I did here. Okay, so our original function is f of x equals x cubed, and we're trying to figure out where f of x equals 10. Okay, we're going to be using the tangent line, and so I'm going to need the derivative, and so I'm going to use the derivative of x cubed. That's pretty easy. That's going to be 3x squared. Okay, now I started off with a point. I'm going to call my original point x naught. We chose 2, and then from 2, we know that the value of the function at 2 is 8, which is not too far off from 10. It's not horrible. And then we're going to use the derivative 2 because we need to figure out the tangent line. And so plugging this in, we get the equation of the tangent line to be y equals 12 times x minus 2 plus 8. And then I set the tangent line equal to 10. We want to know where this equals to 10. And so again, we're using the fact that the tangent line is a good approximation of the function there. And so wherever this x value, whatever x value gets us to 10, this is going to be close to what the x value for the function is. And so from here, we're just trying to solve for x. So how would we get to x? Well, let's move the 8 over to the other side. Now we're going to divide by 12. And last, to get x by itself, we're going to add 2 to the other side. Right? And so notice here, 10, this is the number we're trying to get. And then this 8 here, this is coming from the value of the function at 2. We're dividing by 12. This 12 is coming from the slope. That's coming from the value of the derivative. And then the 2, the plus 2 we have at the end, that's coming from the original point that we started at. Okay, and so this gives us our x value. And if you simplify this down, we get that x is equal to 2 1/6. And so let's call that value x1, same as we did before. So 2 1/6 is the same thing as 13/6. And then we ran through this process again. Okay, so I'm plugging in to get the value of the function. So if I plug in 13/6, if you work this out, cubing it, you get that it's 2197 divided by 216. And the derivative, it's plugging 13/6 into 3x squared. You simplify it down and you get 169 over 12. And then get the tangent line, and there's fractions here, but really it's no more difficult than it was before. The fractions don't really change things very much. And then same as before, in place of y, we're going to stick 10 in there. And so here's we set the tangent line equal to 10, and we're going to solve for x again. And it's the same process as before. We're going to move the 2197 over 216 over, divide by the 169 divided by 12, and then lastly, add 13/6. And so that's what we get. And so again, this 10 is coming from, this is the value we're trying to get. We're trying to figure out where f of x equals 10. The 2197 over 216 is coming from the value of the function. The 169 over 12 is coming from the derivative. And the 13/6 is coming from, that's the point that we were starting off from. That's the point where we calculated the tangent line from. Okay. And if you plug this in, you get the value of x to be 2.154503. And then if you go and calculate out what the cube root of 10 is, or you cube this number, you get that it's 10.0009598. And so if you notice, we have this right over here to 3 decimal places. And so that means that at least the first 3 decimal places, probably the first 4 decimal places, are accurate over here. And so this is already, after just running through this twice, we have come up with a pretty accurate one. What would we do to make it more accurate? Well, we would just run it through this process again. Okay, and each time that we run it through, we would get a more and more accurate, we would get more and more decimal places correct to what is the actual cube root of 10. And so this is a trick that, as I said at the beginning, this is a trick that Newton came up with. It's called Newton's method. It has been used for hundreds of years. It was perhaps more impressive before there were calculators. But actually, a lot of calculators actually use Newton's method to when they spit out the decimals that they have there. And so this is still very relevant. And this is something that still people use, mathematicians and physicists and engineers use when they need to get accurate approximations. Okay, so let's run through exactly what Newton's method is doing. Okay, so again, our goal is we're given some function f of x, and the idea is f of x is some function where it's easy to plug things into f of x. It has a nice derivative as well, because we're going to need to have values of the derivative of f of x, but maybe it's very difficult to invert. And so the classic thing that Newton used this for, and that's most often used for Newton's method, is trying to solve, say, roots of polynomials is something that this is very efficient for. So you have some f of x that's a polynomial, and your value k would be 0. And so one common use, you have some polynomial f of x, and you want to find x values where f of x equals 0. And so these are functions where it's very easy to plug things into polynomials because all you're doing is adding and multiplying and taking powers, which is really just multiplying. And derivatives is the same thing, but it's actually can be very difficult to actually kind of invert polynomials and sort of given a certain y value, figure out what the right x value is. That's actually a fairly difficult problem for polynomials. Pretty much any polynomial higher than degree 4. That's actually a pretty difficult question. And so here, but let's do this for a general value k. And so we're trying to find an a. We're trying to approximate the a such that f of a equals k. Okay. And so we're going to do it the same way that we did it before. We're going to start off by making a guess. Let's call this guess x0. And then once we have x0, we're then going to calculate the value at x0 and the value of the derivative of x0. And we're doing this because we want the tangent line there. And so we get the equation of the tangent line. So remember, in all of this, x0 is a real number. And so really the only variable on this right-hand side is the x. The x naught and the value of x naught at f and f prime, those are all numbers, decimals that we've calculated out. Next, we're going to take this tangent line and we're going to replace y with k, and then we're going to go through and solve for x. And so this is plugging k in for y, and then same process that we had before where we're solving for x. We're going to bring f of x over, divide by f prime, add x naught at the end. And so we get this nice formula for x out of this, where it's x naught plus k minus f of at the point divided by the value of the derivative there. And so again, if this is done, we're trying to find where the function is equal to 0, we just plug in 0 for k here. So it would be even simpler than that. And then we're going to call this new value out of this our x1. And so x1 is going to be x naught plus k minus the value of the function x naught divided by the value of the derivative at x naught. And then if we want it more accurate, we're going to repeat the process with x1. Okay, so let's run through this with one more example. We're going to try and estimate the value of the natural log of 20. So natural log, this is the inverse function of e to the x. And so really, we're trying to find the x value such that e to the x equals 20. Okay. And so our function is going to be e to the x. We want to know when e to the x equals 20. And then we're going to use the fact that the value of the derivative of e to the x is just e to the x again. And so that makes things simple. And so our function, our first guess, I'm going to guess x naught to be 3. I think that may be pretty close. And so then we run this through, and x1 is going to be 3. And so 3 is coming from x naught. 20 here is coming from k. And then 20 minus e to the third. The e to the third is coming from f of x equals e to the x. And so that's minus f of 3. And then the e to the third on the bottom, this is coming from plugging in the derivative. 3 into the derivative. Okay, and so this is the same formula that we had before. And we get that our x1 is actually pretty close to 3, 2.9957413, blah, 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 blah. And so you see that our 3 actually seemed to be a pretty close guess because our next guess that we get is very close to it. And so then we run this through again. And so I just spit out the decimal here, but really to get x2, this is really just running the same process before, where you're starting off with x1 and then plugging x1 into the function and its derivative and calculate it out. And then we get this x2, and if you notice between x1 and x2, these seem to be accurate to 4 decimal places, almost 5. but 4 decimal places. And so that's telling us that those first decimal places are probably correct. In Newton's method, if you get a number of decimal places that stay the same, usually that's telling you that those decimal places are right. And then if again, our x3, well, you see our x3 is essentially the same as x2. The only difference between these two is the 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 decimal places goes to 10 decimal places. And so that probably means that now those 10 decimal places are probably correct. In fact, this isn't always true, but this is generally what happens. If you notice that between the first and the second, we got 2 decimal places. And then the second and the third, we got 2 more decimal places. And then after that, we seem to get, the next however many decimal places to be correct. That probably means that we have all of these correct, plus at least 2 more, because we've always been getting at least 2 on every round. And if you actually plug in what the natural log of 20 is, you'll see that this is correct. Just running this 3 times through, we got this correct to 9 decimal places. 9 decimal places. And in fact, if we did it a couple more times, plugging this in, if we had a calculator that would spit out enough digits, we could probably get this up to 20 decimal places. Well, in the 60s, when they sent the Apollo program, when they sent astronauts to the moon, they figured out that they really just needed things accurate to about, somewhere between 13 to 16 decimal places. And so we already have 9 here. If we ran it a couple more times through, we'd be at that. So we'd be accurate enough to send people to the moon. So that is all for this video. I hope to see you again soon.